Meldes string experiment. The aim of the experiment is to find the frequency of a given tuning fork using Meldes string method. Meldes innovated this method to find the frequency of tuning forks of low frequency which cannot be calculated using conventional methods like sonometer or resonance column experiments due to practical difficulties. Franz Meldes gave a striking demonstration of the stationary waves set up in a vibrating string. Let us discuss the thought process of the genius which led to this new approach. The vibrating tuning fork is an oscillator. The natural frequency of the tuning fork can be directly measured. Yet another but much easier way is to couple the harmonic oscillator to a medium that could carry the waves produced by the harmonic oscillator and by measuring the wave properties at resonance. But wave parameters cannot be easily be measured for a traveling or propagating wave. Somehow we need to stop them or allow them to stand so that we could make measurements on them. The concept standing waves is due to Franz Meldes in 1859. He coupled the harmonic oscillator to a stress string and created standing waves or stationary waves. Franz Meldes used a light thread with one end attached to the prong of an electrically maintained tuning fork and the other end connected to a weight after passing over a grooved wheel which acts like a rigid boundary. A make and break arrangement in circuit makes the tuning fork vibrate. The vibrating tuning fork is an oscillator and it conveys the corresponding wave motion to the string which is coupled with it. A rigid surface for a mechanical wave is like a specular mirror for light. It reflects the mechanical waves. Hence, wave generated in a stress string will be propagated through it only to get reflected from the rigid surface on the other end, namely the pulley. Thus, we have two identical waves which travel in opposite directions, incident wave and the reflected wave. These identical waves but with pi phase difference traveling in opposite directions interfere to form standing waves. The wavelength of these waves could easily be measured from the harmonics of the stationary waves thus produced. First, second and third harmonics are shown in the figure. The velocity of mechanical oscillations through a medium like stress string is equated to its elastic properties and linear mass S. Frequency is 1 by 12 root of T by M, where T is the tension in the string and M is the linear density, which is the mass per unit length. L is the length of the vibrating segment of the string. In the primary mode, the length of one segment corresponds to half the wavelength. In higher order modes, the wavelength changes but it will follow the same relation if we measure L as the length of one segment of the harmonics form. Vibrating tuning fork can give rise to standing waves in the string. When the string is loaded by weight attached at its ends, the tension in the string increases, which in turn increases the frequency of the string, where the same increase in tension in the string lowers the frequency of vibrating tuning fork by increasing the damping of the fork. Standing waves formed in a string have large amplitudes when the damped frequency of the tuning fork resonates with any one of the harmonics of the string. Experimental arrangement. Two coupling methods, transverse and longitudinal coupling. In transverse coupling, the vibration of the prongs of the tuning fork are in a direction at right angles to the length of the string. The time during which the tuning fork executes one vibration, the string also completes one vibration in transverse coupling. Now, if the thread of length L vibrates in one loop, the frequency of the string is given by 1 by 12 root of T by M, where M is the linear density and T is the tension. For N loops, it will be N times 1 by 12 root of T by M. Longitudinal coupling. In this case, the tuning fork is set so that the vibrations of the prongs are parallel to the length of the string. The time duration in which the tuning fork completes one vibration, the string completes half vibration. So the frequency of the thread is half the frequency of the tuning fork. Electrically maintained tuning fork. The chief parts of the electrically maintained tuning forks are the prong, the electromagnet, the spring, and the platinum tip at which the contact is made. The vibrations of the fork are maintained by the intermittent current that flows through the electromagnet placed between the prongs of the tuning fork. When the current flows through the circuit, the electromagnet is magnetized and the prongs are pulled inwards and the steel spring fails to make any contact with P. So the circuit is broken and consequently the electromagnet fails to pull the prong, which falls back and the contact is readme. In this way, the fork makes the vibrations by the circuit a make and break arrangement. Procedure. The electrical connections are made as shown in the figure. The string is arranged horizontally with its length parallel to the prong of the fork. In transverse coupling, the fork vibrates in a direction perpendicular to the length of the string. A mass of about 50 or 60 grams is placed in the scale pan. The circuit is closed. The fork vibrates. Transverse stationary waves are formed in the string. The length of the string between the prong and the pulley is carefully adjusted by moving the fork so that a number of well-defined segments are formed in the string. Leaving the segments at two ends, the length L of the string for a definite number of segments N is measured. The total mass M at the end of the string is noted. The value of tension, which is the weight at the free end of the string, is calculated. The experiment is repeated for different masses in the scale pan. Then the frequency of the tuning fork is calculated using the formula. Longitudinal coupling. The apparatus is arranged as shown in the figure with prongs perpendicular to the string. Then the fork vibrates in a direction parallel to the length of the string in the longitudinal mode. The experiment is performed exactly as before for different masses. Then the frequency of the fork is calculated using the formula given by N by L root of T by M. The frequency is calculated for transverse and longitudinal coupling using the tabular column shown. The mean frequency from the two modes of coupling gives the frequency of the tuning fork.